Anthony Raj. He has pursued his bachelor's, master's and MPhil in physics. He then went on to pursue his PhD in physics at the University of Madras as well. He then went on to work as a lecturer at Thiruvalluvar Arts and Science College and Idya Engineering College for Women. Since the year 2006, he works as the lecturer and assistant professor at Loyola College, Chennai. With regard to research, he has published several papers in international journals, namely Radio Wave Propagation over Salem, Linear and Non-Linear Optical Properties of Pure and Doped Selenium Malate Single Crystals, and many more. He has also attended several conferences and seminars, namely International Conference on Materials Science and Technology, National Conference on Higher Education at Crossroads held at Loyola College, National Seminar on Crystal Growth 12 held at VIT University, and many more.
Welcome to UGC lecture series B.Arc Mathematics Semester 1 Lecture 13. In this lecture, we are going to see Cauchy-Euler homogeneous linear differential equations, then equations reducible to linear differential equation with constant coefficient, then legendary homogeneous linear differential equations. This Cauchy-Euler homogeneous linear differential equation can also be said as Cauchy homogeneous linear differential equation or Euler homogeneous linear differential equation. Like that, different names are there for this Cauchy-Euler homogeneous linear differential equation. Let us see the Cauchy-Euler homogeneous linear differential equation. We know linear differential equation, an equation which has differentiation of a function and the function or linear combination of the first degree of differentiation of the function and the function is a differential equation. Here an nth order linear differential equation is given, that is in the form of a naught x power n dn y by dxn, where this dn y by dxn denotes the nth derivative of y with respect to x plus a1 into x power n minus 1 into d power n minus 1 into y by dx power n minus 1. Here n minus 1th derivative of y with respect to x is considered, then this x is raised to the power n minus 1 plus a2 into x power n minus 2 into d power n minus 2 into y by dx power n minus 2 plus a n y is equal to f of x. This is the general form of linear differential equation. In this equation, this a1, a2 till an are all constants, and this f can be either a constant or a variable or functions of x only. This equation is called as Cauchy-Euler homogeneous linear differential equation or Cauchy linear differential equation or Euler linear differential equation. In this equation, you can notice that the index of x and the order of differentiation are equal. So, the index of x and order of derivative is same in each term of the equation. This equation can be represented in simplified form, that is in operator form, by considering the symbol d is equal to d by dx and d square is equal to d square by dx square, etc. d power n is equal to d power n by dx1. Then that equation, this equation will change to a naught x power n dn plus a1 x power n minus 1 into d power n minus 1 plus a2 x power n minus 2 into d power n minus 2. Here this d power n minus 2 says the n minus 2th derivative of the given function y with respect to x. This is what we assumed in the earlier step, d is equal to d by dx, d square is equal to d square by dx square, then d power n minus 2 is equal to d power n minus 2 by dx power n minus 2 plus etc. a suffix n into y is equal to f of x. The above equation is the simplified form given in operator form of Cauchy-Euler homogeneous linear differential equation. This equation can be reduced to a linear differential equation with constant coefficients. This reduction can be done by taking some steps. Equation reducible to linear differential equation with constant coefficient. To get the equation reducible to linear equation with constant coefficient, we need to do some substitution. That substitution is let x is equal to e power z. After simplification of this x is equal to e power z, we will get logarithm of x, that is natural logarithm of x is equal to z, so that dz by dx will be equal to 1 by x. Keep this as equation. So, equation 3, because in the earlier slides we kept equation 1 and equation 2. So, let us keep this as equation 3. This is obtained by simply differentiating this logarithm of x is equal to z with respect to x. Now, using chain rule for differentiation, we obtain dy by dx is equal to dy by dz into dz by dx, which is equal to this dy by dz will be as it is, then this dz by dx is equal to 1 by x into dy by dz. So, instead of this dy by dx, you can substitute 1 by x into dy by dz. Now, define this d by dz as a new operator, d1, dy by dz is equal to d1. So, we get x dy by dx is equal to dy by dz, because this dy by dx is nothing but 1 by x into dy by dz, which is equal to x dy, which is equal to d1y. So, this is how a new operator can be substituted to get the equation reducible to a linear differential equation with constant coefficient. Proceeding in the same way for the second derivative, similarly for the second derivative we get d square y by dx square is equal to d by dx of dy by dx, which is equal to d by dx of 1 by x into dy by dz. This dy by dx value is 1 by x dy by dz. This is what we obtained in the earlier step, which is equal to minus 1 by x square into dy by dz plus 1 by x into d by dx of dy by dz. This step came by this differentiation. Here this 1 by x into dy by dz is considered as uv. So, differentiation of u into v with respect to x gives u dv plus v du. So, we got this step. Now, simplifying this step, we will get minus 1 by x square dy by dz plus 1 by x into d by dz of dy by dz into dz by dx. So, this is the step we get after simplifying this one. So, again one more dy by dz differentiation is there. So, that is done in this step. Further simplification of the above step gives minus 1 by x square dy by dz plus 1 by x square into d square y by dz square. So, here we have x square d square y by dx square is equal to d square y by dz square minus dy by dz. So, this is the thing we get after simplification. Now, we know that x square, this d square by dx square can be taken as the operator square d square y, which is equal to d1 into d1 minus 1 into y, because we assume that d by dz as a new operator d1 that is used here. So, we got d1 into d1 minus 1 into y. Similarly, we can write for the third derivative, that is similarly x cube d cube y is equal to d1 into d1 minus 1 into d1 minus 2 into y. So, earlier we got x square d square y, which is equal to d1 into d1 minus 1 into y. Now, we got x cube d cube y, which is equal to d1 minus 1 d1 minus 2 into y. Like that we can write for x power 4 d power 4 y, which is equal to d1 minus 1 then d1 minus 2 into d1 minus 3 into y. Like that we can write till nth thing. In general, that x power n d power n y can be written as d1 into d1 minus 1 into d1 minus 2 etc. goes till d1 minus n plus 1 into y. So, till this you got substituting the above values of x, xd, then x square d square y, then x cube d cube y in equation 1 we get, substituting the values we get a0 d1 into d1 minus 1 etc. then d1 minus n plus 1 plus etc. plus a suffix n minus 2 into d1 into d1 minus 1 plus etc. a suffix n minus 1 d1 plus an into y is equal to f of e power z. Because in the starting of this derivation we assume that x is equal to e power z. In the Cauchy-Euler homogeneous linear equation, the right hand side of the equation is f of x. So, instead of that x, e power z is substituted. We got f of e power z. Let us keep this as equation 4. This equation is a linear differential equation with constant coefficients. This equation can be solved by various methods. Now, we will apply this concept in a problem. Solve the differential equation x square d square plus x d minus 4 into y is equal to 0. So, this is linear differential equation of Euler, Cauchy-Euler. this equation can be solved by the following way. Solution to this linear differential equation is obtained by converting the equation into operator form. So, in substitution, by substitution, first we need to substitute x is equal to e power z. Then differentiate to remove this exponential part, we need to take log on both sides of this equation assumption. So, you will get log x is equal to z. Then in the earlier derivation we have learnt xd is equal to d1, then x square d square is equal to d1 into d1 minus 1. We can substitute all those formula here. So, xd is equal to d1 and x square d square is equal to d1 into d1 minus 1. Then substitute all these things in the given equation. The given equation will reduce to d1 into d1 minus 1 plus d1 minus 4 into y is equal to 0. Simplifying this, that is multiply this d1 inside and manipulate that, you will get d1 square minus d1, this d1 is multiplied inside, plus d1 minus 4 into y is equal to 0. This minus d1 and plus d1 gets cancelled. So, you got d1 square minus 4 into y is equal to 0 is the equation. Now, you can this is similar to second order linear differential equation. Solution of the second order linear differential equation will be m is equal to 2 comma minus 2. Then these two solutions are distinct and real. So, the complementary function y is equal to c1 e power 2z plus c2 into e power minus 2z. Now, z is nothing but log x. Substituting z is equal to log x, we get the desired solution as y is equal to c1 into e power 2 log x, then c2 into e power minus 2 log x. So, here this 2 log x minus 2 log x. Here this exponential and logarithm exist. So, this can be written as y is equal to c1 x square plus c2 x power minus 2. So, this is the required solution of the given differential equation, that is Euler Cauchy homogeneous linear differential equation. So, here method of substitution is adapted and we got the solution as y is equal to c1 x square plus c2 x power minus 2. Now, let us do one more problem based on this Cauchy-Euler linear differential equation. In this problem, you are asked x square d square plus y into y is equal to 3x square. Right hand side has got some function. So, let us see how this problem can be solved. Solution, again start with the method of substitution. In the method of substitution, x is assumed as e power z, then the given substituting this x is equal to e power z, the given equation reduces to d1 into d1 minus 1 plus 1 into y is equal to 3 into e power 2z. This is how the given equation will reduce. Then further simplification of this equation will give d1 square minus d1 plus 1 into y is equal to 3 e power 2z. Now the characteristic equation of this second order linear differential equation will be m square minus m plus 1 is equal to 0. Now roots of this characteristic equation, m is equal to 1 plus or minus I root 3 by 2. Here this characteristic equation is not factorizable straight away. So we need to use the formula minus b plus or minus square root of b square minus 4ac by 2a. After using that, we got the roots as m is equal to 1 plus or minus I root 3 by 2. Then the complementary function of the equation will be e power z by 2 into c1 cos z root 3 by 2 cos z root 3 by 2 plus c2 into sin z root 3 by 2. So this is the obtained complementary function. This complementary function can be further simplified by substituting z is equal to ln x. We get the complementary function cf is equal to square root of x into c1 cos the natural log cos of log n of x root 3 by 2 plus c1 into sin of log of x into root 3 by 2. So this is the complementary function. Now let us go to the particular integral. The particular integral of the given differential equation is equal to 1 by d1 square minus d1 plus 1 into the function of x, which is the right hand side of the equation, 3 e power 2z. So here 2 is a, substitute 2 in the place of d1, we get 1 by 2 square minus 2 plus 1 into 3 e power 2z is equal to e power 2z. So after simplification of this, we get e power 2z. So we got the complementary function and the particular integral. So combining both, you will get the complete solution of the given differential equation. Hence the desired solution will be y is equal to root x into c1 cos of ln of x root 3 by 2 plus c1 into sin ln of x root 3 by 2 plus x square is the complete solution of the given differential equation. So in this problem, first we started with a substitution, x is equal to e power z. Then we got the auxiliary equation, then we got the complementary function, then we went to converting that complementary function in terms of x, then resubstituted z is equal to logarithm of x, then we went to a particular integral, then particular integral value is e power 2z. Combining the complementary function and particular integral, we got the desired solution for the given differential equation. Next, Legendre's homogeneous linear differential equation. This Legendre's homogeneous linear differential equation is also a kind of differential equation where instead of that a naught, a plus bx is exist. So a linear differential equation of the form a plus bx to the power n a naught d power n plus a plus bx to the power n minus 1 into a1 d power n minus 1 plus a plus bx to the power n minus 2 into a2 d power n minus 2 plus etc. plus an into y is equal to f of x. This is the form of Legendre's homogeneous linear differential equation. The only difference between Cauchy-Euler homogeneous linear differential equation and Legendre's homogeneous linear differential equation is this a plus bx to the power n. In Cauchy-Euler equation, instead of this a plus bx, only a alone will exist. Here a linear combination is exist, a where a, b, a1, a2, an are all constants, and f is either a constant or a function of x only. This equation is called as Legendre's homogeneous linear differential equation. You can notice one more thing in this equation, that is the index of a plus bx to the power n and the order of differentiation will be the same. Here the index of a plus bx and the order of derivative is same in each term of that equation. This equation can be solved by introducing a new independent variable as we have introduced in Cauchy-Euler homogeneous linear differential equation. There e power x is assumed as z, e power x is assumed as z. Then to remove that exponential, that logarithm is taken, then that logarithm value will give log n of z is equal to x, like that we got. But here a plus bx should be taken as z. Then we proceed as we have proceeded in the Cauchy-Euler homogeneous linear differential equation. We will get the solution for this Legendre linear homogeneous differential equation. So this lecture we got the explanation about Cauchy-Euler homogeneous linear differential equation and Legendre's homogeneous linear differential equation. So in this lecture we learnt about Cauchy-Euler homogeneous linear differential equation. Cauchy-Euler homogeneous linear differential equation can be reduced to constant coefficient linear differential equation by the method of substitution. In the substitution, x is substituted as e power z, x is assumed as e power z, then mathematical manipulations are done, then we got the Cauchy-Euler homogeneous differential equation with a constant coefficient. Then solution of this homogeneous linear differential equation consists of complementary function and particular integral as the linear differential equation, solution of linear differential equation has. Then Legendre homogeneous linear differential equation. In Legendre homogeneous linear differential equation, we have a plus bx. Instead of a plus bx is there. That can also be solved by the method of substitution. There, instead of this x, a plus bx is equal to e power z can be substituted. Then the Legendre homogeneous linear differential equation can be solved. These are all the concepts we learnt in this lecture. So after listening to this lecture, you can answer the following questions. Solve x cube d cube plus 3x square d square minus 2x into d plus 2 into y is equal to 0. Write Legendre's homogeneous linear differential equation. Then solve x cube y double prime plus x y prime minus y is equal to 3x power 4. These questions can be answered. Thank you.